Hello students, this is Chanel Popat. Let us discuss stress distribution today. Stresses are very much important to understand soil and structure interaction. Stresses are induced by structural loads, or we can say weight of the buildings on the earth. It is very much important to predict settlement of buildings, water retaining structures, embankments, bridges, etc. to know its life or to know risk assessment. Generally, soil stresses are derived from elasticity theory. Theory of elasticity generally deals with stresses and strain relationships. It is assumed that stresses and strains are directly related. Under small stresses on the soil and fortunately on the field, magnitudes of the buildings and structures are small in terms of soil. We can utilize theory of elasticity and stress-strain relationship. Let us understand furthermore in this chapter geostatic stresses. So, geostatic stresses means the vertical stress due to self-weight of buildings on that. Now, in general terms, if we can see the residential, of commercial, office buildings, etc., the buildings give more load compared to bridges, embankments, etc. loadings on that soil. Now, let us understand the geostatic stresses more thoroughly through this figure. Here, this figure is showing a soil layer and I am applying load on the building and these green lines are showing ground line. So, this is my ground line. The building is stated over the ground line and it is applying some load. Now, if I want to find out at this plane, which is stated up to Z depth, and if I analyze that, the stresses induced there will be sigma Z. I am telling vertical stress as sigma Z. If I analyze it in the plan, so in the plan there will be horizontal stresses like sigma x, sigma y, sigma y. So in all three axes load will be acting. Actually on the field there will be in all axes load will be acting. Let us understand vertical stresses first. So I am telling sigma z as vertical stress. So sigma z may be written as gamma into z. Gamma is unit weight and z is depth. Whichever depth at where I am finding my stresses value, that is my depth z. Now horizontal stresses. Horizontal stresses sigma x is equal to sigma y is equal to k0 into gamma into z. Here I am writing sigma x is equal to sigma y because they both are acting in perpendicular direction to vertical stresses. Now I can also write gamma into z as sigma z. So sigma x is equal to sigma y will be k0 into sigma z, where what is k0? K0 is mu upon 1 minus mu, that is Poisson's ratio. Let us move further from geostatic stresses. The theories regarding stress distribution. In stress distribution topic, there are mainly these theories which are very much fundamental for this chapter. First one is Boussinesq's theory. Second one is Westergaard's theory. Third one is Newmark's influence chart. Fourth one, that is pressure bulb concept. And fifth one, that is contact pressure concept. Let us understand them one by one in this chapter. So, taking first and very pioneer theory of this chapter, that is Boussinesq theory. Let us understand assumptions for Boussinesq theory first. Then we will go to theory and then we will move further. So, first assumption is soil mass is elastic medium and E, that is constant, as we have talked, theory of elasticity will be used here. And soil mass is assumed as elastic medium, not plastic medium. It is assumed as elastic. Soil mass is further assumed as semi-infinite. It is not infinite, it is semi-infinite. So we can measure everywhere the depth of soil. We are assuming this thing. Soil should be homogeneous. Homogeneous means it is made up of all same constituents, and that is why it is homogeneous. Soil is isotropic. Isotropic means every soil grain is having same elastic properties on all the directions. So if I applied the load from any direction, it will have same characteristics. Every soil grain will have same characteristics. Self-weight of the soil is neglected. So we are assuming zero self-weight. Soil initially should be stress-free. We are assuming soil as stress-free on initial count. We are assuming stress as zero on initial count. And top surface of the medium should be free of shear stresses. So there is no shear stress on top surface of the soil medium. So these are Boussinesq assumptions. Let us move to theory. Boussinesq theory. So Boussinesq gave theoretical solutions for stress distribution in elastic mediums taken as soils through concentrated loading. We can also state this as geostatic stresses, or we can say the vertical stress induced by self-weight of buildings. Here, with this example, let us understand Boussinesq theory. In this example, this red square is assumed as soil surface, and this point O is assumed as under concentrated load Q. And let this point, let us say P point, be a point where we want to find stresses induced by Boussinesq theory. So here at the point P, there will be three stresses in all three directions, like sigma x, sigma y, and sigma z. Here the sigma r is showing resultant force or resultant stress of all these three for this point. Here at this point, the distance from the load application point O will be capital R, and the depth of this point will be Z. Now this radial area, this radius of that point is assumed as small r. Now if the line joining resultant and vertical line, there will be angle beta. Let us understand this by equations. Boussinesq gave equation of vertical stress, or we can say geostatic stress, sigma z as 3 by 2 q by pi cos beta by r square, where r is capital. Capital R will be under root x square plus y square plus z square. Here z square is this, x square and y square is not shown here. But we can also take x square and y square as r square. So we can take capital R is equal to under root r square plus z square. Now sine beta can be written as, here sine of angle beta can be written as small r upon capital R, and cos of angle beta can be written as z upon capital R. Now Boussinesq gave sigma z equation as sigma z is equal to sigma r into cos square beta. Now putting value of sigma r here, sigma z becomes 3 by 2 q by pi cos square beta, cos cube beta by r square. Now if I put cos cube beta value here, sigma z will be 3 by 2 q by pi z by r cube upon r square. Here multiplying r with the denominator, sigma z will be 3 by 2 q by pi z cube by r raised to 5. Now if I multiply z square on upper and bottom both the sides, we can take sigma z as 3 by 2 pi q by z square z raised to 5 upon r raised to 5, and we can take z by r raised to 5 as common. Now sigma z can be written as 3 by 2 q by z square z raised to 5 upon the r is under root r square plus z square. So we can write r square plus z square raised to 5. Here sigma z is equal to 3q by 2 pi into 1 by z square, and in bracket 1 by 1 plus r by z square raised to 5 by 2. So this is just the mathematical calculation. If you simplify the equation, you will get this equation back. It is also written as sigma z is equal to ib into q by z square. ib is Boussinesq constant. ib is equal to 3 by 2 pi into 1 upon 1 plus r by z square raised to 5 by 2. Let us understand ib, Boussinesq factor or Boussinesq constant importance. Value chart of Boussinesq coefficients. This is the graph which is showing values of Boussinesq coefficients. Now, if you are having r by z at every distance, like r and z ratio has radial distance and depth both, so we can find out ib at every point. And after finding out, we have prepared a Boussinesq coefficient table. It can be used in various problems in the field. Let us move further to limitations of Boussinesq equation. So, first limitation is, in the Boussinesq solution, it is assumed that the soil mass is an elastic medium. As the soils are far from being purely elastic, it is questionable to take it as an elastic medium. Second limitation is Boussinesq solution is only applicable when there is constant ratio between stress and strain. But when the stress decrease occurs, like when the stress is decreasing, then the stress and strain will not be elastic in the actual field. So we can question that. In deep sand deposits, the modulus of elasticity increases with an increase in depth, and therefore Boussinesq solution will not be applicable in deep sand deposits. So these are limitations to this theory. Let us understand vertical stress distribution on a horizontal plane. Now, if the Q concentrated load is applying here and R by Z distance is having 1, 2, 1, 2 on both the sides, we can see the stress distribution like this. Now, how we will get to this? We can write Boussinesq equation sigma z is equal to ib into q by z square. Here, if r by z value is 0, then it will be 0.4775 q by z square. Same way, furthermore, however, the value of r by z will increase from 0, the value of sigma z will going to be decrease. So we can prepare the chart like this, and it is showing a table of variation of sigma z with r at constant depth z. So r by z is 0, then ib will be 0.4775 as we have talked, and if it gets 0.5, it will get 57% of maximum. So it will get up to 57% only, then it will get 17%, and then it will get 1.8% only. So this is how the sigma z will vary with r at constant depth z.